with insulators and conductors, we can now think of new arrangements that give us electrostatic forces. Now, to be clear, these are not new electrostatic forces. It's the same force, the same Coulomb's law, charge, force. It's just the materials give us new ways to make the force, to new arrangements that create the force. And it helps us predict how things are going to behave. So let's look at the case of electrostatic forces on conductors. Okay, so we'll start with the Teflon rod that we know and love. So this is a charged insulator. It's really just here to give us some charge. So if we rub the Teflon rod with our cat fur, then we'll have a nice negatively charged surface. And then nearby, we'll put a big sphere of neutral conductor. Okay. Now I'm going to describe it as though our conductor is a metal. We're going to let's assume it's a metal. So if we have negative charge here, this metallic conductor has free electrons in it. So they want to get as far away from these negative charges as they can. So the free electrons will feel a repulsive force and they'll go to this side. Since it started out neutral, that will leave this side positive. Okay. Now notice in a lot of cases, it doesn't actually matter if it's the electrons, the negative charge, or the positive charge moving. If this were a conductor with positive charges that were mobile, then it would be attracted, come this way, and it would leave this side negative. So it doesn't actually matter. But if we want to think microscopically about a metal, what really happens is the electrons build up here, which leaves exposed nuclei over there. Okay, so the charge will separate. And now, if we want to think about the forces, well, these charges will feel a repulsive force here. So we could call that force repulsive. And these positive charges will feel an attractive force on this side. So force attractive, like that. So the question is, what is the net force? So it's feeling forces in both directions. We're not going to calculate it numerically, but if we look at it, we can realize that the force attraction, which I'm just going to write as the magnitude, is greater than the force of repulsion. The magnitudes are greater. And the reason is it's closer. So remember, Coulomb's law depends on the two charge quantities divided by the radius squared, or the separation squared. And this has a smaller separation. So since it's divided by a smaller number, it's bigger. This is farther away. It has a larger separation. So really, it's that this is much bigger. So the conductor is attracted to the Teflon rod. Now, it doesn't even matter which charge the Teflon rod has. Okay, so say we had a different kind of rod that was positively charged, and we put a neutral conductor nearby. The positive charge is going to repel, or let's leave it a metal. If we put a neutral metal here, the positive charge is going to attract its electrons like this, and that's going to leave this side exposed with positive charge. So everything's reversed, yet the forces remain the same. This is the attractive force region here, and the separation is small, so it's a big force. This is the repulsive side. The separation is big, so it's a small force because of Coulomb's law. So it doesn't matter what kind of charge is where. Neutral conductors are always attracted to charged objects. Now, the conductor can become charged, and that can change things. So yeah, keep in mind, you can charge a conductor. But a neutral conductor, where all that's happening is a charge is rearranging, will always rearrange in a way to be attracted to a charge nearby. So I can show you that this is true with our Teflon rod. So here is a Teflon rod here, and I've got the fur here to charge it up in a minute. And now we need a conductor, and for the conductor, I'm going to go with these. So I was a child in the 70s, and in the 70s, Christmas trees were decorated with these icicles. They're little strands of conducting material, and they were very fun to play with as a kid, and then they disappeared for a very long time. I think it's because they were made out of lead. right? And kids would go to the tree and try to eat them, and that's not good. So, but then suddenly, 2 years ago, I'd actually searched for them for many years. 2 years ago, I'm at Target, and they've got just a huge wall of these things. I think they basically found a cheap way to make Mylar and cut it up into tinsel. So I was all excited. I bought like 20 of these things. So I now have enough tinsel to last me forever in demos. But the point is, it's a conducting material, and it's very thin. So if there's a force on it, we will see the force because the material will actually deform and bend and move around. So I'm going to take just one of these out, and I'm going to charge up the rod like this. All right, and I'm going to take my icicle here, and oh, see, there it goes. It really wants to touch the charged rod. Right in there. Anywhere. It says, let me touch it anywhere. So the charge in the icicle is being redistributed, and if this thing is negative, then the negative charges in the icicle are being pushed towards me, which leaves the other end positive, so it's strongly attracted toward the rod. Just like we predicted over there.